Welcome to section 4.2, inflection points. So we're going to start off with defining what an inflection point is. So an inflection point, well, this is a point at which the graph of a function changes a concavity. Alright, so for example, if we had a function that looked something like this, alright, then at roughly this point right here, we change from being concave up on the left-hand side to being concave down on the right-hand side. Alright, so this point would be an inflection point. Alright, so we can find inflection points by finding the point at which the second derivative is 0. So, to find an inflection point, we need the second derivative to be equal to 0, and we need to check the sign on either side. Check that sign of the second derivative changes on either side. So in our little drawing up here, on the left-hand side, our second derivative is positive, right, because we're concave up. And on the right-hand side, our second derivative is negative because we are concave down. Alright, so our second derivative changes signs at that inflection point. So let's look at our first example. We want to find the inflection points of this function g of x. Alright, well, we need the second derivative in order to find our inflection points. So we need to take two derivatives here. So we want g prime of x, we need our first derivative, so that will give us 4x cubed minus 3x squared minus 6x. And then we need our second derivative, so we get 12x squared minus 6x minus 6. So this is our second derivative. Alright, we need our second derivative to be 0. So we're going to set equal to 0 and solve for x. So we have 0 is equal to 12x squared minus 6x minus 6. We can go ahead and pull a 6 out of here. So we end up with 2x squared minus x minus 1. So if we divide by 6, we'll get 0 divided by 6, which is just 0. Left with 2x squared minus x minus 1, which we can factor. Alright, so we want to factor this right-hand side into two binomials. So we will have 2x plus 1 over here, and then x minus 1 over here. Again, we need to set each one of these equal to 0 separately. So we have 2x plus 1 equals 0, and also x minus 1 equals 0. So on the left-hand side, we'll go ahead and subtract 1, and then divide by 2, so x is negative 1/2. And then on the right-hand side, we'll add 1, so we get x is equal to 1. Alright, so these are possible inflection points. Possible inflection points. Need to check sign on either side. Alright, so we still have to look at our second derivative on either side of each of these points just to make sure that we do actually change sign. Alright, so I'm going to come up here just for space. So we're going to check x is equal to 1 first. So we want to check the second derivative on either side. G prime, double prime of 0 for the left-hand side. A 0 makes our calculation pretty easy, right? We get 12 times 0 squared minus 6 times 0 minus 6. Well, that gives us negative 6. So we have a negative second derivative on the left-hand side. And then if we want to check right-hand side, we can look at x is equal to positive 2. So we get 12 times 2 squared minus 6 times 2 minus 6, which gives us positive 30. So we have negative over here, positive over here, so our second derivative does indeed change signs at x is equal to 1. So x is equal to 1 is officially an inflection point. So x equals 1 is an inflection point. And now we need to check x is equal to negative 1/2. Well, on the left-hand side, we can go ahead and look at x is equal to negative 1. So we'll check second derivative of negative 1. We get 12 times negative 1 squared minus 6 times negative 1 minus 6. And we end up with positive 12. All right, so this is positive. And if we want the right-hand side of x is equal to negative 1/2, well, we could do 0. And we already know what g double prime of 0 is. We know that it's negative. So g double prime of 0 is negative. So we change from positive to negative at x is equal to negative 1/2. So x is equal to negative 1/2 is also an inflection point. Alright, and now we have completed that problem. So example 2 asks us to graph a function that meets the following criteria. So we have several points here. First, we need to find and don't worry about these capital F of x, it was just the way I typed it. It automatically capitalized it. Alright, so f of x has a critical point at x is equal to 4. It has an inflection point at x is equal to 8. The value of the first derivative is negative to the left of 4, but positive to the right of 4. And the value of the second derivative is positive to the, it's supposed to be left of 4, or left of 8, and negative to the right of 8. Alright, so let's go ahead and draw ourselves some axes here. I'm going to label x is equal to 4 and x is equal to 8 because those seem to be the main points here. So f of x has a critical point at x is equal to 4. So this is where the derivative is 0, right? Derivative at 4 is equal to 0. So we know that our function is just going to be kind of flat, right about x is equal to 4. Alright, it could be the bottom or the top of a curve, but it's going to be just a little bit flat right there. Okay? Then we know that f of x has an inflection point at x is equal to 8. Okay? So we have to change concavity. Change concavity. Right? That's what our inflection point means, is we change concavity at that point. So somewhere along x is equal to 8, we need to change concavity. Next, we have the value of f prime is negative to the left of 4 and positive to the right of 4. So a negative derivative means that our function is decreasing All right, so we are decreasing on the left-hand side of 4, but we are increasing on the right-hand side of 4. All right, so we're still increasing even over here. Okay, and our second derivative, this is our concavity. It's positive to the left of 8 and negative to the right of 8. So a positive second derivative means that we are concave up. So we have concave up to the left of 8, even over here. And we are concave down to the right of 8. All right, so now we have to try to draw something that matches with all of our criteria. I'm going to go ahead and use a different color and attempt to draw this out here. So I'm just going to start from some point over here. All right, we must be decreasing but concave up. So decreasing and concave up, and we got to level off at x is equal to 4 because we have a critical point there. So we have a horizontal derivative. And then we have to be increasing and concave up over here. So we are increasing. Ooh, I'm going to need some more space. I foresee some problems. All right, that's fine. Concavity got cut off. Concavity. There we go. All right, so now we are increasing and concave up, increasing and concave up. Well, here we have hit our x is equal to 8 line, which is where we need to change concavity. But we still have to be increasing, and now we are concave down. So now we're still increasing, but now we've changed concavity. All right, so this is an example. All right, there's several different graphs that could meet this criteria, but this is the one that I have come up with. All right, and we have met all 4 of the points necessary. So we're now done with example 2. All right, so example 3 asks us to find all critical points and inflection points for this function. F of x is equal to x times e to the negative x. All right, so our critical points are where our first derivative is 0. So we need to go ahead and take our first derivative. Well, we're going to need a product rule here, aren't we? We have this derivative of 2 functions of x. We have x times e to the negative x. All right, so let's go ahead and break out this product rule where we have the derivative of the first. So if x is the first, derivative of x with respect to x is 1 times the second, e to the negative x, plus the derivative of the second, which would be negative e to the negative x times the first. So we end up with e to the negative x minus e to the negative x times x. And if we just want to clean this up, we can go ahead and pull out an e to the negative x and just be left with 1 minus x here. It just looks a little bit cleaner. Okay, so if we want to set this equal to 0, because that's how we find our critical points where our first derivative is 0. So we have 0 is equal to e to the negative x, 1 minus x. Okay, so we'll have 1 minus x is equal to 0. Go ahead and move x to the other side, so we get x is equal to 1. This is a critical point. All right, e raised to a power can never be 0. So that's why we are not worried about that right now. Okay. So we have x equals 1 is our critical point. Well, next we're supposed to find the inflection points, and that deals with our second derivative, right? So let's go ahead and take the second derivative. Well, that's the derivative of the first derivative, right? So e to the negative x, 1 minus x. We could go through and multiply this and then take the derivative, or we can use the product rule again here and look at e to the negative x as our first function. So the derivative of e to the negative x is negative e to the negative x times 1 minus x plus the derivative of the second, which is just negative 1 times the first, e to the negative x. And so we'll get negative e to the negative x plus x e to the negative x minus e to the negative x. And we have like terms here, so we can go ahead and add them together, which will make a negative 2 e to the negative x plus x e to the negative x. And if we wanted to clean this up similar to the first one, we could pull out an e to the negative x and be left with x minus 2. Alright, so our inflection points are possible where the second derivative is 0. So again, we need to set our second derivative equal to 0. Again, we have e to the negative x, which can't ever be 0, so we end up with 0 is equal to x minus 2, which gives us x is positive 2. Alright, so we need to check either side of our possible inflection point. So this is a possible inflection point. So we're going to check when x is equal to 1. So we'll look at it's not g, it's f, the second derivative of 1. Well, our second derivative is what we found right here. That's an x. There we go. So evaluated at 1 gives us e to the negative 1 x minus 2, but x is 1. So we have 1 over e times negative 1, which is going to be negative. Okay, and then we'll check x is equal to 3. So we have the second derivative at 3 is e to the negative 3 of 3 minus 2, which gives us 1 over e cubed times positive 1, which is going to be positive. So since our derivatives, our second derivatives do change sign on either side of x is equal to 1, or on either side of x is equal to 2, x equals 2 is an inflection point. And our last example for today, we need to determine if the function f of x is equal to x to the fourth has any inflection points, and if so, state where. So, inflection points call for a second derivative. So we have f prime of x is going to be 4x cubed, and f double prime of x is going to be 12x squared. We want to set that equal to 0 is equal to 12x squared, and that gives us x is equal to 0 is a possible inflection point. All right. But we need to check either side of x is equal to 0. So we're going to check x is equal to -1. So we'll look at the second derivative evaluated at -1, and we get 12, -1 squared. Well, -1 squared is +1 times 12 gives us 12, which is positive. And then we'll check x is equal to +1. So the second derivative evaluated at +1 gives us 12 times 1 squared, which is 12. So again, it is positive. So since our sign does not change for our second derivative, it is positive on both sides of x is equal to 0. X equals 0 is not an inflection point. Alright, so that wraps up section 4.2. Please take the comprehension quiz and email me with any questions.